Before the 20th century, the most widely accepted understanding of the atom came from John Dalton's atomic model, introduced in 1803. According to his theory, atoms were fundamental indivisible particles that made up all the matter in the universe. Different kinds of atoms combined with one another to form compounds, explaining the wide variety of materials we encounter in everyday life. As simple and logical as this model seemed, it wasn't without its flaws. Over time, scientists began noticing observations that didn't fit Dalton's theory, leading to questions like whether atoms were truly indivisible. By the late 19th century, those doubts had grown stronger. Then in 1897, a groundbreaking discovery by an experimental physicist completely changed our understanding of the atom. His work not only challenged Dalton's model, but also opened the door to a new era centered around subatomic particles. JJ Thomson. Thomson's interest in physics began at a remarkably young age. At the age of 14, he enrolled at Owens College in Manchester, one of the few universities at the time that offered courses in experimental physics. During his studies, Thomson quickly impressed his maths professor. Recognizing his potential, the professor encouraged him to apply for a scholarship to Trinity College, which Thomson successfully earned. After earning his scholarship, Thomson remained at Trinity College for the rest of his career. He received his bachelor's degree in mathematics in 1880, and from then on, he dedicated his life to teaching and researching electromagnetism, following in the footsteps of renowned physicist James Clerk Maxwell. In 1895, Thomson shifted his focus to one of the biggest scientific mysteries of the time, cathode rays. Like many other physicists, Thomson wanted to settle an ongoing debate about what these mysterious rays actually were. One group of scientists believed cathode rays were produced by the ether, an invisible weightless substance thought to fill all of this space, almost like a universal medium. Others argued that rays were actually made up of electrically charged particles. Thomson set out to uncover the true nature of these rays, to determine what caused them, and finally put the debate at rest. To investigate, he used a Crookes tube fitted with several key components. A cathode and anode were placed at one end of the tube, while two opposite charged electrical plates were positioned near the other end. Far end of the tube was coated with phosphor, so it would glow whenever the rays struck the glass. After experimenting with different arrangements of electrical plates, Thomson noticed something interesting. Whenever the cathode rays passed between the plates, they consistently bent towards positively charged plates. To make sure this behavior wasn't caused by something else, Thomson repeated the experiment several times. He used different metals for cathode and anode, and even changed the type of gas inside the tube to eliminate those variables. The rays always bent towards the positively charged plates. From this, Thomson concluded that the cathode rays had to be made with negatively charged particles, which he called corpuscles. Although this was already a remarkable discovery, Thomson knew there was still more to uncover. He continued the experiments, but this time he replaced the electrical plates with large electromagnet. The setup allowed the rays to travel between two magnetic poles as they moved by the tube. By carefully measuring how much they deflected in both the electric and magnetic fields, Thomson was able to calculate the mass to charge ratio of these newly discovered particles. The result was astonishing. The ratio was incredibly small, and his calculations showed that the corpuscles had a mass of roughly 1/2000th that of a hydrogen atom. With this evidence, Thomson announced his findings to the scientific community, proposing that the corpuscles were tiny, negatively charged subatomic particles present inside every atom. Over the following years, several scientists carried out additional experiments to verify Thomson's discovery. One of the most notable was Philip Lenard. Interestingly, Lenard received the Nobel Prize a year before Thomson, a decision that has remained controversial among historians. Even so, Thomson was awarded the 1906 Nobel Prize in Physics for his outstanding theoretical and experimental research on the conduction of electricity through gases. Following the discovery of electron, Thomson introduced his famous plum pudding model of the atom. In this model, tiny negatively charged particles were thought to be embedded within a large sphere of positively charged, much like raisins is scattered through the pudding. Although this model would later be replaced by more accurate atomic theories, Thomson's work marked a major turning point in our understanding of matter. His experiments not only challenged the long-held belief that atoms were indivisible, but also confirmed the existence of subatomic particles, laying the foundation for modern atomic physics. What once seemed like a mature and nearly complete field of science was suddenly transformed into an exciting new area of research, opening the door for many of the discoveries that followed.